we'll start. This is enough people. So, thanks for coming, guys. We're talking about chemistry. And hopefully we can keep it interesting. So we talked about, for people who haven't here, we kind of started with just theoretical science, and we moved to kind of physics, and then forces, and now we're sort of moving to matter. And then the idea is to progress into stuff that we do. So like biology will be next, and so first we'll learn chemistry, and then biology will become neurobiology, and then hopefully we'll talk about psychiatry, right? That's the goal, but I just want to get some basic fundamentals down so we can reference these things when we get to the level of thinking people. So that's the main idea behind it. So, people have very different backgrounds in this stuff. So I'm going to ask lots of just dumb questions, and some questions are probably harder, but who knows what this is?
The periodic table.
Okay. And people can use the periodic table in lots of different ways, right? We can just see, oh, you know, what element number is carbon, and just get basic information from it. But if you understand how the periodic table is made, you can extract a ton of information from it. So I picked this one because I think it's a really good learning example. There's lots of colors, and they're not just random colors, they're colored for a reason, so like-colored things have similar properties. I'm not going to go into a lot of the periodic table, but I do want to go over some basics, right? So this number here, do you guys know what that number refers to? The number of protons in the nucleus of the atom. Okay, so I'm just throwing these jargony terms out so that when I say them, we kind of all know what we're talking about. Do you know what this number means? The atomic weight. And what's the atomic weight determined by? Protons and neutrons, that's correct. And the reason that it's not an even number is that there are different numbers of neutrons possible in nature, and this is the average. If we were to just take carbon, you know, this is 12.011. So most of it's 12, but there's some 13, there's some 14. Obviously very little because it's not making a huge impact. So carbon has mainly, a typical carbon would have 6 protons. Always has 6 protons. Protons determine the element. And how many neutrons?
6.
How many electrons?
Oh, that's
6. Okay. Because it's electroneutral. So electroneutral means that the number of what is equal to what?
Protons, electrons.
So protons, positive charge, electrons, negative charge. Neutron has an atomic weight of 1 but no charge. Just basic stuff we're throwing out here. Okay. Let's see if I can make this work. Oh, I can't. Okay, that's all right. So, I can't draw on this, but you can maybe see the mouse. Hydrogen, carbon.
Put that pen thing at the bottom?
Oh, yeah. There you go, thank you. Pen. Oh, thank you. So, hydrogen, carbon, nitrogen, and oxygen make up how much of our body by weight? Random guesses. 96%. Okay, so we are hydrocarbon, nitrogen, and oxygen. Okay, that's what we are made of, pretty much. The rest of it is, you guys could probably guess. Sodium, right when we draw a Chem 7, potassium, calcium, silicon, phosphorus, no, not silicon. We do not have a lot of silicon in us. Phosphorus, sulfur, and so we do have sulfur in us. It's probably, of all of these, probably the least, but we have appreciable amounts of sulfur. I don't know the exact number. If you count these, this makes up what percent of our body? So more than what percent?
96.
Obviously more than 96%, 99.6%, okay? So this is what we're made of, and then the rare exotic kind of element like iron or that sort of thing, right? Okay, so let's look here at lithium. Does it only pop up when I let go? Oh, okay, it only pops up when I let go. Lithium is what?
a salt.
It's a salt. Well, lithium itself is not a salt. Lithium down in nature would be a salt. What's a salt? These are all kind of just like old generic.
positive and a negative charged ion?
That's right, it's an ionic formed compound, usually with a positive and negative, so like lithium chloride or something like that, that we would see that has a differential charge on it. So in nature it would be found as a salt. Lithium carbonate is typically what we would give patients. So I'm kind of getting at the idea of it's a drug, right? And I always kind of ask this, what's a drug? And it's this vague term, we just use it, but lithium is it's an atom, it's an element, okay? So when I say, you know, where is lithium broken down in the body?
It's not.
It's not, okay? So it's excreted by the kidneys is what you're getting at. But we think about, you know, lithium's not going to be broken down by anything, right? You can't. That would be alchemy. It's literally, lithium is 3 protons and 4 neutrons and 3 electrons, right? You're not going to break that down. You're not going to metabolize it. So it sort of lets you think about things, and the reason I'm mentioning that is I want us to be able to apply basic concepts as well as possible to extract data. So don't memorize, just sort of conceptualize. Who knows what this is? I'm not going to have enough time to finish this, so we'll pick it up a bit. Who knows what these are?
The electron cloud
They're
formation.
electron shells, right? This is where the electrons go, so there would be a cloud of electrons in here. How many electrons go in each of these? So these are called orbitals, okay? They're electron orbitals, but that's what you're getting at. I saw it.
Oh, 2.
2, okay, right. So in here, how many electrons?
2.
So in here,
2. 2.
so in the entire P sort of orbital, how many are there?
4. 6. Oh, 6.
6.
I meant like
Yeah,
in
good.
carbon. Oh.
Yeah, okay.
Alright.
So what we can do by using this is, what's the order that it goes in? What's the order that electrons fill these? So it's 1s, 2s, 2p, 3s, 3p, but we don't have to memorize that, okay? Because we can use our Fermi periodic table to sort of look at it. Because you can see here, this is stable. This is a stable valence shell, right? So 1s, 2 electrons fills this. 2s, 2p is 2 plus 6 is 8, right? Fills this, that's a stable electron shell. We come back down here, 3s, 3p fills this, 4s, and now we can't do p anymore, we have to do d. And so again, you don't have to memorize the order, the electrons, the periodic table, you can extract it from it. So just this idea of using information to multiply encode it to kind of understand these concepts. You can look at a periodic table and look at the orbitals, and you don't need to know all of the information to extract all the information. And that's really more important than anything I'm teaching you. It's just a way of thinking of gathering information conceptually so that other information can be taken from it without learning it. And the more you can do that in medicine, the better off you're going to be, because there's way too many facts. The literature out there is just exploding. You're not going to know it. It's only going to get worse. You want to have a good, solid conceptual basis and expand that conceptual basis. And that's what I think real knowledge is. So we fortunately only have to think about 1s, rather S and P orbitals, because that's all that our body is, right? Looking at this, we're not really getting into the other orbitals. But I do just want you to look at this. And when I see things like this, I just think about kind of chaos in nature. And I talk about this a lot. But when you see patterns like this, going from simple to more complex, but in a beautiful way, like you can tell there's an order to this. It's hard for us to imagine what the next level after F would be, but likely you could mathematically model it by sort of taking these things. And it's common to see as you drive a system harder, meaning as you're pushing harder on a system with whatever the variables might be, you will see these flipping, right? So it's not a gradual transition. It is a flip in transition states. So this is what you would see sort of in a liquid going to a gas or a solid. It's not a gradual thing. There's a fast shift into a whole other state when pressure is added to a system. And I just think that they're very cool. I like that sort of thing. Okay, so I'm just going to draw some stuff really quickly. I'm glad I have a pen. Okay, here we go. I'm going to be fast about this. So we're going to draw carbon. I don't know if you guys remember. How many electrons does carbon have? How many protons does it have? How many? 6. Good. So how many electrons does it have?
6.
6. Okay, so how many in the first valence shell?
2.
2. So this one gets filled first, okay? I can't draw this very well with this thing here. All right, and so then, how many in the outer shell? 4, so there's 4 left, okay? And you don't pair until you have all of them, until you have 1 electron in each orbital, right? So in here, we have 1 electron in the 2s orbital, and then 1 electron in each plane of the p orbitals, right? So, what is the valency of carbon? It's just kind of a definition thing. The valency is the number of unpaired electrons.
0.
So it's the number of the number of unpaired electrons in the outer shell.
4.
4. So this is the valency of 4. Why does that matter? What does that tell us?
It can make 4 bonds.
It can make 4 bonds. That's what we're really looking at. So I'm going to go quicker with this. Well, let's just do oxygen, and I'll use it. That's an O. It's hard to differentiate it from a circle, but here, we'll make it a happy oxygen. So how many in the first shell? 2. Okay. Well, first question is, how many electrons does oxygen have?
8.
8. Very good.
It's coming back to me.
So how many are going to be in the outer shell?
6.
Okay, and how should I draw them? Should I draw?
So 2 in pairs, and then the other 2 not paired?
Do you all agree with that?
Yeah.
Okay, I agree with that too, which means that it must be right. Okay. So let's go ahead and draw hydrogen. Okay, what does hydrogen have?
1.
1, in which valency?
First.
The first one, right? There's those there. Okay. Okay. So, here's hydrogen again. So this is how it works, right? We don't draw things this way, but this is kind of what's happening, right? So what molecule is this here? Water. And I draw water for a reason. Why?
Makes up most of our bond.
Water is everything, right? In biology, it's water chemistry. We do water. We really are water. Our chemistry is water chemistry. All right, so what's this? It's water. Okay, what is this?
Oxygen.
It's an oxygen.
Hydrogen.
Hydrogens, okay. So is this a charged molecule?
No.
All right.
4.
Oh, okay, so we're drawing, so is it charged or not? I'm asking the question because it's a terrible question. But one thing I say a lot is we want to think functionally and not reductionistically. Okay, so it's a complicated question. It's not H2O positive, right? It's not charged in the sense of having a formal charge, but it has relative charges. Okay, so I'm asking you the questions in totally loaded ways, and you're answering them correctly because that's what you've been able to be taught to do, and you're all very smart at answering test questions. I'm trying to just sort of make us think more just functionally at what's kind of going on. So where does the charge exist here? Where is the charge here?
Where the bonds are.
Okay, you're right, there is charge where the bonds are, but where are the relative differences in charge? Where do they exist? Okay, so oxygen is going to be what kind of relative charge? Negative. How come?
Why?
Yeah, why? This can get really deep, but just from a, I'm sorry?
Doesn't have like unpaired electrons.
The paired electrons are on the outside there, away from the hydrogens, which causes that relative negative.
It wants electrons more, is the bottom answer. And it's really a thermodynamic thing, which gets really complicated, but it just wants electrons more. Hydrogen is happier not having the electrons more so than oxygen. And that's, I mean, it's not something I think we can intuitively know. That's just really it. It's just, it has more of an affinity for electrons. So a relative negative here and a relative positive here. If water was linear, would it be polar? Water's not linear, right? I don't remember, I think it's a 104.5 degree bond angle. But if it were linear, if this was an 180 degree bond angle, would it be polar? How come?
Because the paired electron groups wouldn't be able to be together.
Well,
Because isn't that what's happening? Is that on the oxygen you have those? If you look at the clouds, the 2 paired electrons would be out here, relative to that drawing. Isn't that what makes it negative? Relative to negative, whereas the hydrogen still
yeah,
have.
actually, I will agree with that. I think you're right. I'm thinking of it a little bit differently, but I think you're right. I think you're saying it a different way. I think
no
you're right. I want
electrons
to
on
think
that,
about
at the bottom of that.
the way that I think about whether something's polar or not is I just draw the electric dipoles, or rather the electric angles, right? We have one going this way and one going this way. And when they sum, when you add them, the lateral components cancel out, and you have a net sort of dipole. If dipoles were like this, they would completely cancel out, and you would have no dipole. I think that that follows from what you're saying. I can't wrap my head around it right now, but I think you're right. So it's very important that this is polar, and that's going to be sort of what the most of this talk is about, is whether things are polar or not polar and what that means, right? Because what matters in chemistry, what matters in life? I've said this like a lot, so you haven't here, you wouldn't know it. But what are the two things that determine kind of everything? Going back to physics, what is the force that does everything? We heard gravity. Now, gravity is a fine force, but it's not what we're interested in. We don't talk about gravity when we talk about chemical reactions. What do we talk about?
Is it attraction?
Attractions. What gets attracted? Charge, right? Charge. We're talking about electrodynamics. So what we're concerned of is charge and shape. Charge and shape is going to determine how things interact. Is pretty much what really every process that we look at in life is getting at. Okay. So this is getting at the same thing. All right. So this is called the space-filling model, the electron model. This is a ball and stick model. What is this charge here? And this is, okay, so I want you to kind of imagine water now. Okay, this is where it gets really like cheesy. But hold water in your hands and kind of feel it, right? It has a shape, it has relative charges. It has properties to it that we can kind of get comfortable with, right? If we were to put other water molecules in here, they don't interact randomly. It's going to want to do certain things, and that's kind of what we're getting at. Now, I want you, as much as possible, to use as many senses as you can to understand stuff. And I think that that goes a long way into learning, and that, one thing I see a lot is like, when you're learning, write. I don't want you to take notes in here, but it's really useful when you're learning to write, because we're learning in multiple ways, and it's the same thing as sort of multiply and coding stuff. So this kind of shows us here, if we take a step out, we have different waters. They're not interacting randomly, right? They're orienting in a certain way. And what are these things here that we're seeing? What are these representing? You guys haven't kind of done chemistry in like years, but they're hydrogen bonds. That's right. And hydrogen bonds are really what power things, right? Hydrogen bonds are what lets most of our proteins and the things in our body do the cool things that they do, DNA, etc. So I want you to imagine this and go back to this sort of good cell picture that we saw with all the water everywhere. And I also, again, I had to kind of keep bringing these things up. I want you to think about things in the molecular world, which is in a million scale, okay? So everything is a million times bigger. So a cell is the size of this room, right? Water, do you guys want to guess how big water is roughly? Bigger or smaller than a meter?
Seriously?
In the real world.
Oh,
Smaller. Bigger or smaller than a millimeter?
smaller,
Bigger or smaller than a micrometer?
smaller,
Bigger or smaller than a nanometer?
smaller, bigger.
So we're getting close, right? At least we have a sense of, it's right there. It's an angstrom, which is a tenth. An atom is typically an angstrom, a carbon atom. They can get bigger. So this is going to be roughly 2 to 3 angstroms, which is 0.2 to 0.3 nanometers, which is how big in our millionfold world. Making you go back and do all this math that we hate.
So a millimeter?
A nanometer is a millimeter, so 0.2 to 0.3 millimeters. So I kind of want you to see that, okay? It is literally about the smallest distance that you can make between your fingernails and kind of perceive, okay? So that's a water molecule, and this is the cell. And there's a lot of them, right? Billions, I don't really know the calculation. And you've got to imagine, they're not just interacting randomly, they're whipping around with these forces, carrying momentum with them. Okay, so what's going on here? What's this?
Salt.
Salt, sodium chloride, table salt. What do you think these are? Water. Okay, so what's sort of happening here?
It's dissolving.
It's dissolving, right? This is getting at dissolving and the idea of hydration shells, okay? So we want to think about happy hydration shells. So how are these things orienting? It's not randomly how they're orienting, right? How are they sort of orienting?
Based on charges.
Based on charges, that's right. And so if there is a charge difference, water can dissolve things, right? So that's when we say, can water dissolve something? Water will dissolve things. F, it can. So we think about polar versus non-polar. What dissolves in water? Polar things or non-polar things? Polar things, right? And so things that have a relative charge difference. So that's what allows this to happen, okay? It's kind of important for a lot of reasons, but when we think about sort of the size of an ion is carried largely by the hydration shell. So when we think about transporters or just channels, the effectiveness of a channel is not just based on the size of the ion, it's based on the size of the hydration shell. And that's getting into the kind of stuff that we don't really need to know too much about. But let's think about proteins, right? And this is getting ahead of ourselves, we're talking about proteins in the second half. But proteins are made out of what? Amino acids, right? And amino acids can be polar or non-polar, etc. Right? So what do you think when we take an amino acid and we throw it in water, what does it do?
Depends.
It depends, right? But you can imagine, thermodynamically, it wants to put the polar stuff on the inside or the outside. On the outside, right? It wants to put the polar stuff on the outside because that's where it's going to be happier. So you can see that in proteins when we get there to kind of think that way. So I've got water here and I've got salt. And we can dissolve it, and it's not too fancy, but it's going to get at the idea of a couple of things. So pretty much, what happens when, can this dissolve salt indefinitely?
No,
How come?
it gets saturated.
It gets saturated. What does that mean?
No.
I didn't bring a straw. This is called degeneracy. Does anyone know what degeneracy is?
Like impurity? Or?
Degeneracy is when you use something, solve problems with tools that they weren't necessarily designed to solve. And it's why human beings can do really cool things, right?
Because we're degenerates.
Because we're degenerates, absolutely. Degeneracy is probably the highest level of intellect there is, right? You take things and you solve problems. It's kind of the opposite of redundancy, right? Machines solve problems with redundancy. You make 6 of them. If one of them breaks, you've got 5 more. You know, we can solve problems in dozens of different ways and using different parts, which is what makes us kind of cool. I think we still can dissolve more. So, sorry, you were saying it will saturate. Why does it saturate? Just think about it from a nuts and bolts level, right? Why might something saturate? I hope I've run enough salt. What is actually happening when I'm dissolving this? Is the sodium chloride disappearing? Is it alchemizing and becoming something else? So
looks
why
like,
is it ultimately going to stop being able to dissolve this?
Run out of water.
Right, you're gonna run out. It's a very nuts and bolts problem. We're dealing with very real things. We don't like to think about them in these sorts of ways, but yes, it takes a lot of water molecules to dissolve these. Ultimately, you run out of water molecules. There's a set number, and once we exceed that, there are certain ways that we can cheat by putting energy in the system. We won't really get into that. Because you can cheat the number of water molecules required to saturate something. But I want you guys to sort of start thinking in nuts and bolts ways, because they're not that complicated. If you have a conceptual understanding, you can start to answer questions. I can't, yeah, okay. So we definitely have saturated at this point. You can see at the bottom. Not that this is too exciting, but I will just pass it back. I guess what I'm saying is I want you to look at this in a new way, right? You've all seen something dissolved in water, but I want you to look at it and get in there, right? Don't see water, see molecules, right? Think about things differently. There are real processes going on in there that we can appreciate. And so anyway, it's not the most fancy experiment that I've done, but it's just, you know, something that's able to get our hands on it. So again, water chemistry, right? This is how these things work. We do dehydration reactions, we do hydrolysis reactions. That's how most of the things in our body are done, by adding or removing water. I'm gonna pick up some speed. What's this here?
Carbon.
Carbon, right? So we do lots of carbon chemistry. What's its valency?
4.
So how many bonds can it have?
4.
Okay, good. So I'm going to draw a couple things quickly. We don't have much time, so I'm just going to rush through it. Tell me which of these can exist and why. This takes way too long. Yes, no?
No.
No. Why?
Too many.
I'm sorry, why?
Too many.
Too many what? Too many hydrogens, right? So you're exceeding the outer shell. It doesn't want to do that. Yes or no?
Yeah.
Yes, and why? I'm not accounting for all the electrons here. Rather visually, I'm not accounting for them, I should just say. I could. Yes or no? Good, good. Why? What's the valency of nitrogen? You don't have to think of, well, I guess you do.
Three.
It's 3. So we're accounted for here, right? All right, how about this? This will be the last one.
Oh.
Yes or no?
No.
No, how come?
Hydrogen.
Hydrogen, right? We're breaking into a new valence shell. It's not going to want to do that. Okay, that's good enough. Functional groups. Okay, so now we're starting to talk about shape in space. Okay, that is what's going to determine what these things do. Their shape in space. So I'm going to use the analogy of Legos. Okay, they're going to come up over and over and over again. Legos kind of have building blocks, and you can use them in different ways to create lots of different complex things. But kind of when you zoom in, it all comes down to the Lego blocks. And I'll get into more detail there later. I just want to go over through a few quickies. This is an alcohol. Okay, does anybody know what this here is? I didn't draw this, by the way.
Ethanol.
Do you know what these mean? Yeah, ethanol, right? So 2 carbons, each line is a carbon, so C, C, OH, and then they're saturated by hydrogens, okay? What else matters here? The amine, that's common. Ether is just an oxygen between 2 carbons. Sulfide we see sometimes. So an aldehyde is a carbonyl group, which is a C double bonded O at the end. A ketone is a C double bonded O, a carbonyl group between carbons. A carboxylic acid is C double bonded OOH. That's probably good enough there. Okay. Again, this is a Lewis structure, and it's not perfect. It's shoehorning stuff, it's not talking about electrons, and it's not really being honest about what's going on here. Because stuff moves a lot. Let's see if I can draw something. Like, for example, when I draw, that didn't work. Who knows what this is? Who knows what that is? It's just inorganic phosphate. Okay, so it's PO4 2-. But this isn't real. These two things don't exist. It's spinning, right? They're not stable, they're spinning. The electrons are just whipping around. They're not staying here in this way. So there's a solid bond, and then the electrons are just sort of spinning around it. So you can't portray that in a single picture. But most of the time when there's a double bond, and oftentimes even when there's not, it's not fully stable. You're flipping in directions, you're flipping around cis or trans bonds and that sort of thing. So again, we're moving on to the space filling model here. You can kind of see Lewis structure, ball and stick, space filling models. Just want to go through a few of these very quickly, right? So oxygens, here's an alcohol, an OH, right? Here we know what does it mean, so we're going to go over that. Aldehyde, right, like we said, the carbonyl group at the end. Acetic acid, it's a C double bonded OOH. Ketone, it's a double bond in the middle, whatever. The reason that I'm showing this is that you can see these have different shapes and they have different charges, okay? That's all that matters. These are your building blocks. These are your Legos. They're more complicated than Legos, but they fit in certain ways. You can build them in certain ways, and they're not random. They have chemical personalities that let them do things. So we can predict things about them just by kind of understanding their shape. And yeah, that's good enough for that. Okay. Nucleophile, electrophile, it's not even really that important. We can just skip that. All right, so we'll just talk about oxidation, right? So increasing oxidation. This is fully reduced. We add 1 oxygen, or 1 bond to oxygen. It's increasing oxidation. We add a second bond to that oxygen, it's more oxidation. Double bond, OOH, more oxidized, and CO2. As we go up, is this more polar than this, or less polar? Is CH3OH more or less polar than CH4? More polar. Is CH4 polar at all? It's not, it's chiral, so, I mean, it's not chiral, so it's not for sure. But this has an OH, so it's got a relative sort of charge difference. This has more of a relative charge difference. So we're getting more kind of polar. What about up here? Is that polar? Think about it.
It's kind of dense, isn't it? Oh, they add up.
It's linear, right? CO2 is a linear molecule. You can't know that from just looking at it, but water is special. Most things that look like water are actually linear. I don't know why water is so special, but it's very rare for something like water to not be linear when you just look at other elements. But CO2 is linear, so it's nonpolar. What's this? What kind of reaction is this?
Combustion.
It's a combustion. I'm amazed how many people, I would never know these things. I just learned it, is why I can talk about it and pretend like I know something. So it's a combustion reaction. What's happening here? What oxidation, right? But at the same time oxidation happens, what has to happen? Reduction. Why? And that's why we call it a blank.
Redox.
Redox. We call it redox because they happen at the same time. You can't have one without the other. Good. So this is a redox. But what we're interested in is the oxidation of CH4 to CO2. Why are we interested in this? Maybe you're not interested so much, but why is this useful? What does this let us do?
Gas, fuel.
It lets us drive, right? This produces lots of energy. And I'm bringing this up because I think that if we can understand systems, we can manipulate systems, okay? So there are rules to this. There are chemical rules, and we can predict what's going to happen if we change the chemistry, right? So when we think of gasoline, what is the rating that's used? It's an octane rating. So anyone want to guess what octane is? What does octa usually mean?
8 carbons.
8 carbons, right? That's it. 1, 2, 3, 4, 5, 6, 7, 8. Great drawings. So okay, that's octane, right? Octane rating is really getting at like the ability for gas to not knock an engine, which is something that's totally different. And octane's actually got a negative octane rating, but it's breakdown products have a positive octane rating. The point is that our fuels are hydrocarbons, okay? And they get broken down in particular ways to produce a lot of energy. What is actually usually the limiting factor of energy in an engine? This is, I mean, just, do you know this or not? What limits our energy in an engine typically? Oxygen is typically the limiting factor. How fast can you shove oxygen into that cylinder to create an explosion, right? Because we have stoichiometry here, you need to have oxygen to make it move. And heat is another issue, right? So what this is doing displacement work on a piston that's mechanically linked to your car to make it drive, right? You provide more displacement work and you can get more mechanical work. So what we want to do is get more oxygen in there. So we can sort of learn these things, and so that's what a turbocharger does. That's what a larger cylinder does. It lets you shove, and then you get into more complicated things like how much can the metal take and that sort of thing. Nitrous oxide, right? It's not randomly that we found out about nitrous oxide, right? Like Fast and the Furious, NOS. A chemist can look at nitrous oxide and immediately see its application in a car engine. Because what do you think nitrous oxide does? I mean, I kind of told you what the limiting factor is, but it does two things. So, I mean, what do you think nitrous oxide does?
Delivers more oxygen.
It delivers more oxygen. What else do you think it could do potentially that matters in these reactions?
Cool it down.
It does both of those things. So any chemist who sort of understands the properties of nitrous oxide immediately would see its applications in cars. And so it's just getting at this idea of if you understand a system and what sort of factors go into manipulating it, you can go in and scientifically predict what's going to happen and then you can test that, okay? That's what we need to do in psychiatry, and we're very far from it. And I gave the analogy of sort of the balloons before, the colors of balloons. This was a long time ago. When you understand PV equals nRT, you can know every single factor that's going to influence what those balloons do as far as floating or not, and how they're related. And we need to begin experimentally going after those variables instead of just focusing on receptor types and that sort of thing. It's a very narrow view to things. I mean, you have to start somewhere, but I think that we could get a little bit more scientific with it. I hate blowing through discussions. So we're going to take a 1-minute meditation and think about, what it feels like on that level of scale, right? Getting down to seeing the atoms kind of as they are. Just the idea of the cup of water. When we look at things, kind of thinking of them not just as the materials that we're familiar with, but also the materials that kind of underlie it, right? Because when I go back to that periodic table, what can you make with that periodic table? If I took each of those elements and put them in lumps, right, and I gave you enough of them in the bonds that you needed, what could you make?
Put them all together?
If I gave you unlimited supplies of each of those elements, and the chemistry to form whatever sort of bond you wanted, what could you make?
Everything.
You can make the universe, okay? Right, so, I mean, it's sort of a dumb question, but that's what these things are made of. They're these elements arranged in certain ways, in certain orders with other elements. So, to kind of look at things that way, it just gets you thinking a bit differently about things. I sent out an email with a link to Cell. We're going to definitely watch it more than once. I have 15 minutes, so I'm probably going to not watch it. Did anybody watch it? It's got an epic music to it. I'll just sort of open it up for the first time.
This is completely paid by its home remedies.
It's just getting inside a cell where we can kind of begin seeing these properties in action.
Is this the Harvard thing that they did? Or, sorry, is this the Harvard thing? Yeah.
Do you guys know what these are?
Oh yeah, he's one thing.
These are proteins, right? Lipids. We're going to be going through a few of these. We saw some. You know what these are? Carbohydrate chains. It's an extracellular matrix like glycoproteins. So we're going to go into that a lot more in the biology section, but just kind of to oh, that worked. Okay. All right. So we're going to start kind of the second half of the talk and obviously not get through it, but we're going to get back to Legos, right? So you can build an incredibly varied amount of things with Legos, but when you zoom in far enough, it's still an individual Lego there. And that's still fundamentally the connectivity and the bonds that Legos are going to have. They can only do what Legos can do. So we don't build things with Legos. Do you guys know the sort of broad things that we build things with? Our body's broadly made up of like 4 macromolecules. So we'll get there anyways. But I will just show you that with very simple components, you can build amazingly complex things that really are beyond what you would think kind of are their properties. And this is kind of getting at emergence, right? We just have Legos here. But if you put them together in the right way, you can solve a problem. And each of these Legos is only doing what a Lego can do, but when you use them together, you can create sort of a functional emergent property from them. And that's really what the body does. That's what the body capitalizes on, using small things to do very cool things. You guys can get on YouTube and look at all the amazingly just complex things that people build with Legos. People are just geniuses. And if you're really lazy,
Oh my gosh.
How does that not break?
and it's fascinating to think that, you know, in the body we have mechanical equivalents. We have mechanical equivalents for almost everything, and it's sort of, you know, I hate to say we have mechanical equivalents in the body. The truth is we have biological equivalents in the real world. We're sort of solving problems in the real world in a similar way often that biology does. So here are our 4 main groups of macromolecules, okay? Top left, proteins. Top right, bottom left, lipids and fats. Bottom right, nucleic acids, okay. That's right. So these are the building blocks of us. From these 4 things in small molecules, you can make us. And they work in ways that we can kind of predict. So proteins are the big ones, right? Proteins are the workhorses. They pretty much do most of the processes that are really cool in our body. They're made from, you guys already told me, amino acids. How many amino acids are there? 20. There's 20 that we use. There's more, but there's 20 that we use in our body. And they each have a signature, right? They have a chemical signature that when you put them together gives them different properties. And it's not just a simple combinatorial approach. It depends how they all kind of fit together. So it's an alphabet, right? It's kind of like we got 20 Legos with different properties. We have 20 letters that we can make different stuff from, and that changes their properties. Carbohydrates in us is mainly glycogen for storage, for energy. It's also texture, right? So carbohydrates, the frame in this building is made of wood, which is a carbohydrate, okay? It's just carbon, hydrogen chains from the plant. Chitin, like the armor, carapace that insects have, is carbohydrates. It can be extremely strong because of hydrogen bonding. Our extracellular matrix is made of carbohydrates. It's that kind of gooiness. Mucus, when you think about like that gooey texture, yeah, it's lovely. That's carbohydrates, to kind of give you a sense of what it's making. Lipids, I've got a special place in my heart for, because lipids are really at the start of creating organization, right? Phospholipids in particular. Phospholipids create spaces, and if you don't create spaces, you can't have life, right? We are individuals in the Western sense because we are separate from the rest of the world, and that separation came initially from lipids, right? So you create a lipid bilayer which separates water spaces that allow differential concentrations and reactions, and that's what life is, right? We can have a different space inside us than is in the environment, which is very much against, like I talked about thermodynamics. Thermodynamics wants equilibrium. Lipids fight equilibrium. So that's where lipids are kind of cool, and for other things. Nucleic acids are obviously information storage. So this is getting at more of the kind of chemistry side of it, right? So what is this in our broad classes? It's a protein. Okay, anyone want to guess what that is? I mean, I don't expect anyone to guess, but any wild guesses? Okay, it's a serotonin receptor, okay? Here's serotonin coming in. So let's think a little bit. Where is a serotonin receptor? Where is it located? I'm sorry?
In the cell dendrites?
It's in the cell membrane, right, and the dendrites, yes. So at the synapses, which is typically the dendrites, which is in the cell membrane. What is the cell membrane made out of? Lipids. Are lipids polar or non-polar?
Polar.
Non-polar.
So you're okay, a phospholipid, yes, you're absolutely right. In the space between, is that polar or non-polar? Non-polar, and then it's got the polar heads, right? That's very, very good. Similarly to this, right? So knowing that information, knowing where it is, if I said, there's an amino acid here, which amino acid is it? And you might not know the specific one, but which class do you think it would belong to?
Probably non-polar.
Yeah, right, why?
Because it's transmembrane.
That's right, because it's transmembrane. So again, you can think and make sense of things. This is actually important because we can do, and let's say this. What do you think this is? Where do you think this is sitting?
Outside.
It's probably intracellularly if this is, but yes, outside of the lipids. So it's polar, right? So we can begin to think about these things. There's a huge field that's opening up of protein engineering, and we can begin to do really incredible things. And the reason for that is that God has kind of provided a template of lots of building blocks, right? And we see building blocks at every single level. There are themes of nucleic acid sequences that have certain properties. So we can now begin to manipulate stuff in logical ways. We know that there are like selectivity pores, right? So a selectivity pore is what is being selected for whether sodium or potassium or calcium or whatever's going to go through it. We can take that conserved sequence, and evolution, plays on this. It's not random. These things happen in conserved ways. And take a selectivity pore and add it to a receptor, so we can chop this serotonin selectivity off if we know where it is in the gene, insert in whatever we want. And they've done this actually for clozapine. We have a conserved amino acid site for clozapine that we can put instead of this, and now genetically insert these receptors where we want them. So we can begin to engineer receptors. Clozapine's not in the body. So ideally, you can target these to specific places or neurons, give clozapine and create a receptor that sort of works, that does what you want it to do. I think this is going to be a big field in the next 20 or 25 years, sort of mechanically engineering, or rather I should say genetically engineering proteins, because it makes sense. That's what evolution does. We see these families in the way that they kind of expand. They're using very conserved themes that you see sort of over and over. Okay. These, which main group is this? Carbohydrates, okay. Starch and cellulose, right? We know that they're very different things, but are their chemical formulas different? No. So that would make them not esoteric, isomers, right? So they have the same chemical formula. Why aren't they the same thing? Why aren't they the
Alpha
same?
and beta bond.
That's one for alpha and one for beta, that's right, close to medical school. But I don't think that's why are they different? Why do they have different properties?
Because you can break down one of the bonds in your body, you can't break down the other.
Okay, that's right, but why?
Some enzyme thing.
That's right, why? I'm trying to kind of get to the core. Why are they different? What gives things their properties?
Why one's up and one's down? I don't know.
So one is up and one is down, and that is a difference in
Structure.
shape,
Yeah.
in structure, it's shape. So they are different, we know that they're different, and they're going to act differently because they have different shapes, and that matters. Shape and charge is what determines the character of a molecule. It's extremely important, and this is just a great example of that. Starch and cellulose behave extremely differently, same elements, but you put them together in a different way, they do very different things. What about down here? What class is this?
Fat.
Fats, right? Okay, so cholesterol is made in sort of the smooth ER that, it selects the fluidity of the membrane. It's not actually a bad thing. All right, this is a free fatty acid. It's a mono unsaturated fatty acid, right? It's got a double bond. This is the what carbon? If we had to number this, what carbon would it be?
What?
1, okay. So it's the alpha carbon, okay? What's on the other end of alpha? In the Greek letters or whatever. Omega. Okay, so this would be
Oh.
the omega carbon. Yes. Yes. So this is omega 1, omega. This is the omega 9. So this is an omega 9 fatty acid, right? So when we talk about omega-3 fatty acids, what we're talking about is a double bond, a cis double bond, in the omega-3 position, right? And we know how important the differences between omega-3, omega-6, and omega-9 is. A single change in the placement of a double bond completely changes the way it goes down the icosanoid pathway, which is hugely important for inflammation, for heart disease, etc. So these things are important, right? Like the relative chemistries of them are important. Here's a typical triglyceride. It's got sort of a glycerol backbone and then tri-3 fatty acids. Here's a phospholipid. Again, your glycerol backbone, 2 fatty acids, and a phosphate group, sort of seeing it here. And then here again we have DNA, right? Double-stranded DNA. So I will do a couple more slides and then wrap up. So how do we build molecules? How do we do what we do, right? Again, kind of what am I thinking sort of question, but what do we need to do to make stuff?
Bond.
I'm sorry?
Bond.
Bond, yeah. So we have to create bonds in different ways. So we need to create bonds with materials, right? So we have to have the materials. How do we get the materials?
Eat stuff.
Eat. That's right. Eat and breathe is pretty much all that we can do. Or if we don't want to take it out from the outside, what else can we use?
Make it with sunlight.
We can't do that.
No.
But if we're not going to take it out from, if we're not going to take it, you are so good at taking in sunlight. Where's my compliment? So if we're not going to get it from the outside, we're going to get it from the inside, right? So we're going to either take things in or we're going to take things that are in our body and convert them to other things. How do we do that? How do we create bonds?
Enzymes.
Enzymes. What are enzymes?
Protein.
Proteins, right? Anything that ends in ACE is an enzyme. Enzymes are,
Things that catalyze reaction.
right, they're proteins. Proteins are made from,
Amino acids.
which are made from the code which comes from DNA genes, right? Okay, these are all like, what am I thinking? You guys know all this stuff. So you can see that each of these is a different enzyme, and based on what we're making, what cell it's in, what's being produced, we can make different small molecules, okay? So this is how we make things, right? This is how we make everything that is in us. We use enzymes to catalyze certain bonds, and we can make them in certain directions based upon what enzymes our body makes and what it takes in and what it doesn't take in. So it's really not too complicated. I mean, this looks really complicated, but from a basic standpoint, we take stuff in and we convert it to other stuff that we want, or we take stuff that's in our body and we break it down and convert it to other stuff. That's, pretty much it. But enzymes are obviously super important to do that. Here's what this is. It's a ribosome, right? And I got to give a shout out to David Goodsell. He drew that for me. I thought that was very nice. Okay, so we'll end there. Do you guys have any questions before we
What's
wrap
that
up?
one?
I'm sorry?
What's that one supposed to be?
This here?
Yeah.
What's this? Oh, we're gonna think. What's this?
Pneumonia.
An amine. What's this?
Carboxyl.
A carboxyl. So it's an amine.
It's an amino acid.
It's an amino acid. And that's why I want us to start thinking, right? When we start hearing things, they have value, they have meaning. We can extract what this is from a basic understanding of what's going on there. What's an R?
It's a side chain.
That's a side chain. Okay, you guys were a very, very nice crowd. We almost got through it. You guys have any questions? Oh, I didn't share my last experiment with oil.
Let's do it.
All right, let's do it. It's not actually
Everything's changed since lunchtime.
I wish I had, I wish I had phospholipids to show you this, because it's very cool to see. The reason that I wanted to show this experiment primarily is that people want, and you can have the honors. So, what's going to happen when he puts this oil, which is, of our 4 groups, what? Okay, and when we look in here, right, as we look in here, this is a yellow liquid, but what are we actually seeing? Look hard, look real hard.
Clear. I don't know.
If we look real hard, if our eyes could zoom in a million times, what is inside of here? Molecules. What are they? You could draw them, right? We could draw these. What is this?
Hydrocarbons.
It's hydrocarbons. That's right. And what's on the end of it?
Long and tails.
It's a fatty acid. Fatty acid. What's on the end of it?
Cholesterol.
No, it's not cholesterol. It's a fatty acid. What's on the end? It's hydrocarbons with an fatty acid on the end. It's a carboxylic acid on the end. So you draw your hydrocarbon, C double bonded OOH, right? That's what's floating around in here, okay? So you're going to squirt it in here. And what's going to happen and why?
It's going to stay together and not dissolve
And why is it going to stay together?
because the lipid is non-polar and it's just floating around.
Squirt it in the middle of it.
Oh, sorry.
Okay. And so as we watch,
Fat
and it's doing this why? What genes are making it take this form? What gene is making it do this?
None.
None. Well, so how does it know to do that?
It's polar, non-polar.
Okay, I'm getting at the idea that you don't need genes to explain a phenomenon. Most things that are happening because that's what they do. You know, they're looking for what gene determines the way that neurons sort of lace. It's not a gene, okay? It's the way that particles work, right? What makes a potato chip when you cook it have the shape of a potato chip? Like, what gene is that? It's not a gene, right? It's the differential heating when you have skin on the outside and flesh on the inside. The differential heating is going to create that shape. It's just a property of the physics. So you don't actually have to look for answers all the time for like what is doing it. Sometimes that's just the magic of nature. It kind of solves problems for you in very, very cool ways. And that's why you see so much of us in nature, right? Like our hands, our bodies, our lines are mimicking nature. You can see those same things, same patterns in rocks. You can see the patterns in water because we're just following these same equations. But anyways, and I wish we had phospholipids because not only will it will actually create a bilayer, right? So you can actually see a bilayer creating a separate space, which is pretty cool. All right, cool. Thanks, guys.
Thank you.
Watch